Have you ever wondered if the universe itself can die? Not in some violent explosion or catastrophic collision, but in a slow, gentle fading into eternal darkness? What if everything we see, every galaxy spinning through the void, every star burning bright, is simply running down like a cosmic clock? Tonight, we embark on a journey to the end of time itself. Together, you and I will witness the universe's final chapters, and in doing so, we might discover something profound about our own place in this vast, temporary existence. Are you ready to see how it all ends? For most of human history, we believed the universe was eternal and unchanging. The stars were fixed points of light, permanent and immortal. But then we discovered something remarkable. The universe is expanding, growing larger with every passing moment. And if it's expanding now, that means it was once smaller. It had a beginning, and anything that has a beginning might also have an end. This revelation changed everything we thought we knew about existence itself. The universe you see tonight is not the universe that will exist tomorrow, or in 1,000,000,000 years, or in a time so distant that our minds struggle to comprehend it. When Edwin Hubble peered through his telescope and saw galaxies racing away from us in all directions, he discovered that space itself is stretching. Imagine dots on the surface of a balloon as you inflate it. Each dot moves away from every other dot, not because they're traveling through the rubber, but because the rubber itself is expanding. This is how our universe behaves. Every galaxy, every cluster of stars drifting apart on an invisible current. And this expansion raises a haunting question. If everything is moving apart now, will it ever stop? Or will the universe continue to expand forever, growing colder and darker until nothing remains? The fate of the universe depends on a cosmic battle between two fundamental forces. Gravity pulls everything together, trying to halt the expansion and perhaps even reverse it. But there's another force at play, something far more mysterious. We call it dark energy, and it pushes space apart, accelerating the expansion. Think of it as a tug of war on the grandest scale imaginable. For billions of years, cosmologists debated which force would win. Would gravity triumph, causing the universe to collapse back in on itself? Or would the expansion continue forever? The answer we've discovered is both beautiful and unsettling. Through careful observation of distant supernovae, those brilliant stellar explosions that briefly outshine entire galaxies, we made a shocking discovery. The expansion of the universe is not slowing down as we expected, lighting up. Dark energy, whatever it may be, is winning the cosmic tug of war. This means the universe will expand forever, growing larger and colder with each passing eon. The galaxies we see tonight will one day be so far away that their light will never reach us. And eventually, even the stars themselves will go out, one by one, until the universe becomes a vast, dark, and silent void. This scenario has a name. Scientists call it the heat death of the universe, or sometimes the Big Freeze. Despite its name, it's not a sudden event, but a gradual winding down. Imagine a fire burning through the night. At first it blazes bright and hot, crackling with energy. But as the fuel runs low, the flames dim and the coals grow cold. The universe is that fire, and we're watching it in the early hours when it still burns bright. But the fuel is finite. The hydrogen that powers stars, the energy that drives galaxies, all of it is slowly being used up, converted into forms that can never be reclaimed. You might wonder how we can predict something so far in the future with any certainty. The truth is, we can't know for sure. Science is always revising itself as new discoveries emerge. But based on everything we currently understand about physics, about energy and entropy and the fundamental laws that govern reality, It's written into the very fabric of thermodynamics. Energy always flows from hot to cold, from order to disorder. And once everything reaches the same cold, lifeless temperature, nothing can happen anymore. The universe won't end with a bang, but with a whimper. A slow fade to black. But let's not get ahead of ourselves. The universe as we know it still has an incredibly long life ahead. We're living in what cosmologists call the stelliferous era, the age of stars. This epoch began about 200 million years after the Big Bang and will continue for trillions of years into the future. Right now, at 13.8 billion years old, the universe is still relatively young. It's vibrant and active, filled with stellar nurseries where new stars are born and galaxies that dance in gravitational embrace. We're fortunate to exist during this bright and energetic time, but all ages must end. So what will it feel like, this journey to the end? Of course, no human will be alive to witness it. Our sun will die long before the universe does, and with it, any chance of life as we know it surviving on Earth. We can imagine, we can calculate, and we can use our minds to travel forward through time, watching as the cosmos transforms from the busy, luminous place we know into something utterly alien and desolate. Join me now as we take this journey together. Let's watch as the stars go out, as galaxies drift beyond reach, and as the universe settles into its final, frozen stillness. To understand where we're going, we need to understand the forces that shape our cosmic destiny. The universe's fate is determined by its density, by how much matter and energy it contains relative to its size. If there's enough matter, gravity could eventually overcome the expansion and pull everything back together in what we call a big crunch. If there's too little, the expansion continues forever. And if the balance is just right, somewhere in between, the expansion gradually slows but never quite stops. For decades, we thought we lived in that perfectly balanced universe. We were wrong. Dark energy changes everything. This mysterious force, which makes up about 68% of the universe's total content, pushes space apart with ever-increasing strength. We don't know what it is. We can't see it or touch it. We only know it exists because of its effects, because of the way it makes distant galaxies accelerate away from us. Some scientists think it's a property of space itself, a kind of energy that emerges from the vacuum. Others propose more exotic explanations. But whatever dark energy is, its presence means the expansion will not just continue forever, it will accelerate. The universe won't gently coast to a stop. It will race faster and faster into the infinite dark. Imagine you're standing on a beach watching boats drift out to sea. At first, they move slowly, and you can still make out details. But as they travel farther, they seem to accelerate, shrinking faster and faster until they vanish over the horizon. This is what's happening to the galaxies in our universe. The ones we see tonight are drifting away, and the farther they are, the faster they recede. Eventually, they'll cross a cosmic horizon beyond which their light can never reach us, no matter how long we wait. They won't be destroyed or cease to exist. They'll simply be gone from our observable universe, leaving us in an ever-shrinking island of visibility. Within our own local group of galaxies, things are different. Gravity still holds sway here. The Milky Way, Andromeda, and about 50 smaller galaxies are bound together by mutual gravitational attraction. In fact, Andromeda is actually moving toward us, not away. In about 4 billion years, our two galaxies will collide and merge in a slow-motion cosmic dance. But this is an exception, a local pocket where gravity wins. Beyond our local group, dark energy dominates. Every other galaxy cluster, every other cosmic structure is being carried away on the tide of expansion. And as time goes on, even the galaxies in our own group will eventually exhaust their fuel. So we find ourselves in a peculiar position. We're living in a universe that's simultaneously expanding and clustering, dying and being reborn, all at different scales. New stars are forming in nebulae even as old stars die in supernovae. Galaxies merge even as the space between galaxy clusters grows. It's a dynamic, chaotic, beautiful system, but it's also temporary. All of these processes require fuel, require available energy to drive them, and that energy is finite. The second law of thermodynamics, perhaps the most fundamental rule in all of physics, tells us that entropy, or disorder, always increases. The universe is moving from a state of high energy and organization to one of low energy and chaos. Think of it this way. Every star that shines is converting matter into energy through nuclear fusion. Hydrogen becomes helium, releasing light and heat in the process. But you can't reverse this efficiently. Once the hydrogen is fused, that energy is radiated away into space, spreading out and cooling. It can never be fully gathered back and reused. This is why stars have lifetimes. This is why even the universe has a lifetime. There's only so much usable energy available, and every second that passes, some of it becomes unusable, lost to the eternal cosmic background, contributing to the slow heat death of all things. Now you might be thinking, this sounds terribly pessimistic. If everything is doomed to fade away, what's the point? But consider this. The fact that the universe has a finite lifespan, that everything is temporary, makes it more precious, not less. Every star is a fleeting miracle. Every moment of consciousness, every thought you've ever had, exists because of a chain of improbable events stretching back billions of years. We are the universe experiencing itself. Brief sparks of awareness in a cosmos that will one day go dark. And there's a strange beauty in that. We'll explore this philosophy more deeply later. For now, let's continue our journey into the future. The heat death scenario is not the only possible end. There are other fates the universe might meet, depending on what dark energy really is and how it behaves over time. If dark energy grows stronger, it could eventually tear apart not just galaxies, but stars, planets, even atoms themselves in what's called the Big Rip. If dark energy is actually unstable and decays, the universe might collapse in a big crunch after all. But based on our current measurements, based on how we see the universe behaving right now, the slow freeze is the most likely outcome. So that's where we'll focus our attention as we move forward through the eons. Let's step forward in time. Not just years or centuries, but trillions of years into the future. The first major milestone in the universe's decline won't come for a very long time. Star formation, the process by which clouds of gas collapse and ignite into new suns, will continue for another 100 trillion years. That's about 7,000 times longer than the current age of the universe. During this vast span, countless new stars will be born. But there's a catch. Each generation of stars uses up more of the universe's hydrogen, and new hydrogen isn't being created. Slowly but surely, the wells are running dry. The stars being born in the far future will be different from the ones we see today. As hydrogen becomes scarcer, only the smallest, most efficient stars will form. These are the red dwarfs, tiny suns that burn their fuel so slowly that they can shine for trillions of years. In fact, not a single red dwarf that exists today has ever died. They live so long that the universe itself isn't old enough yet for even one to have run out of fuel. These dim, patient stars will be the last lighthouses in the cosmic dark. When they finally begin to fail, the age of stars will be well and truly over. Around these red dwarfs, could life exist? It's an intriguing question. In the far future, as larger stars die off, any remaining civilizations would need to adapt to the dimming universe. They would cluster around the last functioning stars, harvesting every bit of available energy. Perhaps they would build vast structures, Dyson spheres that capture every photon emitted by their parent star. Or perhaps they would learn to hibernate, to slow their processes down to nearly nothing, waking only when necessary to conserve energy. Intelligence might find a way to persist even as the universe grows cold. But eventually, even the cleverest beings would face the same inevitable truth. The fuel is running out. What happens when a star finally dies? It depends on the star's mass. The smallest red dwarfs will simply cool down, fading from red to brown to black, becoming what we call black dwarfs. They'll still exist as solid objects, spheres of spent nuclear ash drifting through space, but they'll emit no light and no heat. Medium stars like our Sun will puff up into red giants first, shedding their outer layers in beautiful planetary nebulae before leaving behind white dwarf cores. And the largest stars will explode as supernovae, either scattering their material back into space or collapsing into black holes. Each type of stellar death contributes to the universe's slow decline as we move further into the future. Past the 100 trillion year mark, star formation finally ceases entirely. The last stellar nurseries collapse without igniting. The last new stars flicker to life and begin their long, lonely vigils. The universe enters what astronomers call the degenerate era, named for the degenerate matter that makes up white dwarfs and neutron stars. During this era, which will last for an almost incomprehensible span of time, the universe's remaining light will come from these stellar remnants and from the dying red dwarfs. The galaxies, those great spirals and ellipses we see tonight, will have long since lost their structure, their stars drifting apart into loose clouds. During the degenerate era, time takes on a different quality. Events that seem impossibly slow by our standards become commonplace. Stars occasionally collide by chance, briefly flaring with new energy before fading again. Planets, untethered from their long-dead parent stars, wander as rogue worlds through the darkness, frozen solid and utterly lifeless. The temperature of space itself continues to drop as the cosmic microwave background radiation, the afterglow of the Big Bang, stretches and cools with the expansion. The universe is growing colder in every sense. Fewer energy sources remain. Fewer interactions occur. Entropy steadily increases. The white dwarfs and neutron stars that populate this era are strange objects. A white dwarf contains about as much mass as the Sun, but it's compressed into a sphere the size of Earth. A neutron star is even more extreme, packing more mass than the Sun into a sphere just 20 kilometers across. The matter in these objects is so dense that a single teaspoon would weigh millions of tons on Earth. They shine not through fusion, but by slowly radiating away the residual heat from their formation. Over trillions upon trillions of years, this heat bleeds away into space. They cool from white to yellow to red to invisible infrared, and finally to absolute darkness. How long does this era last? Conservative estimates suggest the degenerate era could continue for 10 to the 37 years. That's 10 followed by 37 zeros, a number so large it's essentially meaningless to human intuition. To put it in perspective, the current age of the universe, 13.8 billion years, is 10 to the 10 years. We're talking about a period more than a trillion times longer than the universe has existed so far. During this unimaginable expanse of time, the last lights flicker and fade. But even when they do, even when every star and stellar remnant has cooled to match the temperature of space itself, the universe will not quite be dead yet. One more act remains. Let's take a closer look at how stars actually die, because understanding this process is key to understanding the universe's end. Stars are fundamentally simple machines. They're massive balls of gas held together by gravity, with fusion reactions in their cores that produce outward pressure. The balance between gravity pulling in and pressure pushing out keeps a star stable. But this balance can't last forever. Eventually, the fuel runs out. When it does, gravity wins and the star must face its mortality. The manner of death depends entirely on how massive the star is to begin with. Our Sun is a medium-sized star, neither particularly large nor small. In about 5 billion years, it will begin to run low on hydrogen fuel. When this happens, the core will contract and heat up, while the outer layers will expand dramatically. The Sun will swell into a red giant, growing so large that it will likely engulf Mercury, Venus, and possibly Earth. From a distance, it will be a bloated, angry red sphere, no longer the cheerful yellow star we know. This phase will last for about 1 billion years. Then, the Sun will shed its outer layers in a series of gentle puffs, creating a planetary nebula. At the center, a white dwarf will remain, slowly cooling over trillions of years. Larger stars, those with more than 8 times the Sun's mass, meet more violent ends. When these giants exhaust their fuel, their cores collapse in a fraction of a second. The collapse is so sudden and so powerful that it creates a shock wave that blows the star apart in a supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. These explosions are among the most energetic events in the universe. They're also crucial for life because they're the only way that heavy elements like iron, gold, and uranium can be created and scattered into space, where they eventually form new planets and, potentially, living beings. What's left after a supernova? Sometimes, a neutron star, an object so dense that atomic nuclei touch each other, creating a sphere of pure nuclear matter. Other times, if the original star was massive enough, the core collapses beyond even the neutron star stage and becomes a black hole, a region of space where gravity is so intense that not even light can escape. These black holes will play a crucial role in the final chapters of the universe's story. They're the ultimate survivors, the last objects that will persist when all else has faded. But even they are not eternal. We'll return to them soon. The smallest stars, the red dwarfs we mentioned earlier, have the simplest deaths. They'll simply run out of fuel and cool down. No explosion, no drama, just a gradual dimming over time. Because these stars are so efficient, using their fuel slowly and completely, they extract every last bit of energy before going dark. In a sense, they die the most peaceful deaths of any stars. They'll become black dwarfs, objects that have never been observed because the universe isn't old enough yet for any to exist. Their theoretical endpoints, cold spheres of crystallized stellar matter drifting forever through an empty cosmos. By the end of the degenerate era, all normal stars will have died. The universe will contain only these dead remnants, along with planets, asteroids, comets, and the diffuse gas that never coalesced into stars. And black holes, of course. Lots of black holes. Some will be stellar mass black holes, the remnants of massive stars. Others will be supermassive black holes, the monsters that once lurked at the centers of galaxies, millions or billions of times more massive than the Sun. In the dark future universe, these black holes will be the dominant structures, the last objects with any significant gravitational influence. And they'll still be feeding, slowly consuming anything that drifts too close. This brings us to an interesting point. Even in the far future, occasional events will still occur. A black dwarf might capture a rogue planet, briefly heating up from the collision and emitting a faint glow before cooling again. 2 neutron stars might spiral together and merge in a cataclysmic event, releasing a burst of gravitational waves that ripple through empty space with nothing to detect them. These rare occurrences will become less and less frequent as matter spreads out due to the expansion. But they won't stop entirely. The universe will never reach a state of absolute, unchanging stillness. It will just approach it asymptotically, getting closer and closer without ever quite arriving. It's worth pausing to appreciate what this means. The universe's death is not an event but a process, one that unfolds over timescales we can barely conceive. There's no moment where we could point and say, there, the universe just died. Instead, it's a gradual fading, a slow transition from complexity to simplicity, from hot to cold, from light to dark. It's like watching a sunset that lasts for eons. The sky doesn't suddenly turn black. It dims by imperceptible degrees, each moment only slightly darker than the last, until one day you realize that the sun set so long ago you can't remember what it looked like. That's the heat death. Not a catastrophe, but an ending so gentle it's almost peaceful. As we continue our journey through deep time, we encounter one of the most significant transitions in cosmic history. The galaxies, those great island universes that have dotted the cosmos for billions of years, begin to fall apart. This doesn't happen through any catastrophic force. It's simply that the stars within them, no longer bound by the gravitational pull of active galactic centers, slowly drift apart over immense timescales. The spiral arms dissolve. The elliptical structures disperse. What were once majestic galaxies become loose, swarms of stellar corpses spreading out into the void. The universe is losing its architecture. Why do galaxies fall apart? When stars were still shining, their collective gravity in the presence of dark matter kept galactic structures coherent. But as stars die and become cold remnants, they occasionally interact in ways that eject them from their parent galaxies entirely. Imagine a billiard ball collision. Two stellar remnants pass close to each other. One gains energy and speed from the encounter, enough to exceed the galaxy's escape velocity. It flies off into intergalactic space, never to return. Over trillions of years, this happens again and again. Slowly, galaxies evaporate, their members wandering off one by one into the cosmic night. The supermassive black holes at the centers of galaxies will persist longer than the galaxies themselves. As stars are ejected, these black holes remain, patient and hungry. Occasionally, a stellar remnant or rogue planet will wander too close and be consumed, releasing a final burst of radiation as it crosses the event horizon. But these feeding events become rarer and rarer. Eventually, each supermassive black hole will sit alone in empty space, light years away from the nearest bit of matter, effectively isolated. The universe by this point will have become extraordinarily empty, with vast distances between anything that could be called an object. Let's talk about emptiness for a moment. Right now, space seems empty to us. The average density of the universe is about 1 hydrogen atom per cubic meter. That's incredibly sparse. But in the far future, after galaxies have dispersed and the expansion has continued for eons, space will be far, far emptier. The distance between stellar remnants could be millions or billions of light years. If you are somehow conscious and floating in this future universe, you might see absolutely nothing in any direction you looked. No stars, no galaxies, no light of any kind. Just darkness. Pure, absolute, unending darkness. The expansion of space plays a crucial role here. Remember, dark energy is constantly pushing space apart, accelerating the expansion. As the universe grows, the distance between objects increases, even if they're not moving through space themselves. Think of it like dots on a balloon again. As the balloon inflates, the dots move apart without traveling across the rubber surface. This means that even if a stellar remnant is moving through space toward another object, the expansion of space itself is carrying them apart faster than they can approach. In the far future, most objects will be causally disconnected, unable to influence each other in any way. During this era, the cosmic microwave background radiation, that faint echo of the Big Bang, continues to cool. Right now, it's at about 2.7 degrees above absolute zero. In the far future, it will cool to a fraction of a degree, then millidegrees, then less. It will always be there, filling all of space with the faintest possible whisper of ancient light, but it will be so cold and so dim that it carries effectively no energy. The universe's temperature will approach absolute zero, not because something is actively cooling it, but because the expansion stretches and dilutes every form of energy until nothing substantial remains. You might wonder if any structures at all will persist. The answer is possibly. Protons, the particles that make up atomic nuclei, might be stable forever. Or they might not. Some theories suggest that protons can decay, breaking down into lighter particles over incredibly long timescales. If this is true, then eventually even the black dwarfs and neutron stars, made of protons and neutrons, will dissolve particle by particle, evaporating like drops of water in a desert. The timescale for proton decay, if it happens at all, is at least 10 to the 34 years, another incomprehensibly large number. But in the context of eternity, even this is just a moment. If protons do decay, the material remnants of the stellar age will simply cease to exist. Black dwarfs will vanish. Neutron stars will evaporate. Rogue planets will dissolve into their constituent particles and then into radiation. In this scenario, the universe would be left with only photons, neutrinos, and black holes. Photons and neutrinos would be stretched and cooled by the expansion, becoming effectively inert. And the black holes would dominate, at least for a while. These gravitational prisons would be the last complex structures in existence. But as we're about to discover, even black holes are not immune to the universe's relentless march toward maximum entropy. Nothing is truly eternal. Welcome to the black hole era, a period that will dominate the universe's timeline far longer than all the previous eras combined. If protons are stable, this era begins around 10 to the 40 years from now. If protons decay, it starts earlier. Either way, black holes will eventually be the only significant objects left in the universe. They're survivors by nature, immune to the processes that destroy everything else. They don't burn out like stars. They don't decay like particles. They simply exist, warping space-time around them, patient monuments to a more energetic age. But they're not truly eternal. Stephen Hawking discovered their secret weakness. In 1974, Hawking made a revolutionary discovery. Black holes are not perfectly black. They emit radiation. This happens through a quantum mechanical process at the event horizon, the boundary beyond which nothing can escape. Virtual particle pairs constantly pop in and out of existence in empty space. Normally, they annihilate each other immediately. But near a black hole's event horizon, one particle can fall in while the other escapes. From the outside, it looks like the black hole is emitting particles. This is called Hawking radiation, and it means that black holes slowly evaporate, losing mass over time. They're not immortal after all. The rate of Hawking radiation is incredibly slow for large black holes. A stellar mass black hole, with the mass of perhaps 10 suns, would take around 10 to the 67 years to evaporate completely. That's 10 million trillion years. A supermassive black hole with a billion solar masses would take even longer, around 10 to the 100 years. These timescales are so vast that they make previous eras seem like brief moments by comparison. Given enough time, and time is one thing this dying universe has in abundance, every black hole will eventually radiate away all its mass and disappear in a final flash of energy. As a black hole evaporates, something interesting happens. The smaller it gets, the faster it radiates. In its final moments, a black hole will emit energy at an accelerating rate, shrinking faster and faster until it vanishes in a tiny burst of gamma rays and other high-energy particles. This burst would be imperceptible from any distance, a brief spark in an ocean of darkness. And then nothing. The black hole, which may have existed for 100 trillion years or more, is simply gone. Its mass has been converted entirely to radiation, which will then spread out and cool with the expansion, contributing to the universe's ever-increasing entropy. During the black hole era, these objects would be the only sources of new energy in the universe, faint as their Hawking radiation might be. Everything else would be dark and cold. If any form of life or intelligence somehow managed to persist into this era, and that's a very big if, it would need to cluster around black holes to harvest their energy output. Some physicists have speculated about civilizations that slow down their processes to match the available energy, thinking one thought per trillion years, effectively hibernating through the ages. It's a haunting image. It's a haunting image. Conscious beings, if such could exist, witnessing the very last acts of a dying universe. The smallest black holes will evaporate first. Stellar mass black holes, which form from the collapse of massive stars, will begin to wink out after tens of trillions of years. Then, over even longer timescales, the supermassive black holes will follow suit. These cosmic giants, which once anchored entire galaxy clusters, will slowly shrink over timespans that dwarf all previous eras combined. By the end of the black hole era, around 10 to the 100 years from now, every single black hole in the universe will have evaporated. The last one will disappear in a final, lonely flash, and with it, the last significant source of energy in the cosmos will be extinguished. What's left after the black holes are gone? Photons, neutrinos, perhaps some exotic particles we haven't discovered yet. But no structure, no objects, no possibility of complexity or change. The universe will have reached a state of maximum entropy. All the energy that was once concentrated in stars and galaxies will have been spread out uniformly, diluted to the point where it's effectively useless. This is the true heat. Death, the final state toward which everything has been moving since the Big Bang. Cold, dark, featureless expanse where nothing happens and nothing ever will happen again. It's the end of the story, written into the laws of physics. This state has a name in thermodynamics. It's called thermal equilibrium, a condition where everything is the same temperature and no energy can flow from one place to another because there are no differences to drive the flow. It's the end state of any closed system, and the universe, as far as we know, is the ultimate closed system. But here's the curious thing. Even in thermal equilibrium, the universe won't be completely static. Quantum mechanics tells us that random fluctuations will still occur, tiny bubbles of order appearing briefly and randomly in the void. These fluctuations could theoretically, over incomprehensibly long times, create organized structures again. But they'd be extremely rare, separated by times so vast they make our current timescale seem like nothing. Let's take a moment to truly appreciate the timescales we're discussing. The universe as we know it is 13.8 billion years old. That seems ancient to us, but it's nothing compared to the lifespan ahead. If the universe's history so far were compressed into a single second, the black hole era would last longer than a trillion centuries. These numbers are so large that they cease to have intuitive meaning. We can write them down and manipulate them mathematically, but we cannot truly grasp them emotionally. This is a place where human imagination reaches its limits. We're contemplating a future so distant that it's essentially another reality. Hawking radiation itself is a fascinating phenomenon. The particles that escape carry away energy and thus mass from the black hole. This means the black hole gradually loses mass. But here's the strange part. As it loses mass, its temperature actually increases. Smaller black holes are hotter than larger ones. A black hole with the mass of the Sun would have a temperature of about a millionth of a degree above absolute zero. But a black hole, the mass of a mountain, would be much hotter, thousands of degrees. This inverse relationship means that evaporation accelerates as the black hole shrinks. It's a runaway process with an explosive conclusion. Imagine watching one of the last supermassive black holes in the universe. For tens of trillions of years, it would appear essentially unchanged, a dark sphere distorting the faint glow of the cosmic background. Then, imperceptibly at first, it would begin to brighten. The Hawking radiation would become slightly more intense. Over more eons, the brightening would continue, slowly at first, then faster. In the final moments, the black hole would blaze with intense radiation, shrinking visibly, contracting from something planet-sized to something asteroid-sized, to something the size of a house, to something microscopic, until finally, in a flash, it's gone. The last gasp of organized energy in the cosmos. The radiation emitted by evaporating black holes will propagate through space, spreading out and redshifting with the expansion. Eventually, like all energy in the universe, it will cool and dilute until it contributes to the uniform, featureless background. Every black hole's death adds a tiny bit to the entropy of the universe, moving everything one step closer to that final equilibrium state. And once all the black holes are gone, once that last flash has faded, there's no process we know of that can create new sources of energy. The universe's ability to do work, to change and evolve, will have effectively ended. Is there any hope? Any possibility that the universe might avoid this fate? Well, there are some speculative scenarios. If dark energy changes over time, the expansion might stop or even reverse, leading to a big crunch instead of a big freeze. If our understanding of quantum mechanics is incomplete, perhaps there are processes we haven't discovered that could revitalize the universe. Some physicists have even proposed that random quantum fluctuations given infinite time could eventually recreate a new Big Bang. But based on our current understanding, based on the laws of physics as we know them, the heat death appears inevitable. The universe is a clock winding down, and we're just watching it happen. There's something profoundly beautiful and sad about this story. The universe began in a state of perfect simplicity, a hot, dense point containing all matter and energy. From that initial simplicity, complexity emerged. Particles formed, then atoms, then stars and galaxies. The universe became interesting, varied, full of structure and change. But this was always temporary, a brief flourishing between two eternities of simplicity. Before, there was nothing but compressed energy. After, there will be nothing but dispersed energy. The middle, this era of stars and life, is a beautiful accident, a temporary victory of order over chaos that must eventually be reversed. The final evaporation of black holes marks the end of an era, but not quite the end of time. Time itself will continue. Space will continue to expand, but nothing will happen. There will be no events to mark the passage of time, no processes to measure it by. In a very real sense, the concept of time becomes meaningless in a universe at thermal equilibrium. There's no past or future because nothing changes. There's only an eternal now, a frozen moment stretched across infinity. It's the closest thing to true nothingness that can exist while still technically being something. And yet, perhaps this is not truly the end. The laws of physics, as we understand them, don't forbid the existence of the universe in this state. They just say that nothing interesting will happen. But the universe has surprised us before. Dark energy itself was a surprise. Quantum mechanics continually defies our intuitions. Who's to say there isn't something beyond our current understanding, some process or phenomenon that could breathe new life into the cosmos? It's unlikely, but not impossible. And in the face of eternity, even the most improbable events become certainties given enough time. Perhaps the heat death is not an end, but a transition to something we cannot yet imagine. We've arrived at the dark era, the final epoch in the universe's timeline. This is the state that will persist for perhaps eternity, long after the last black hole has evaporated, long after any structure or complexity has dissolved. The dark era is characterized by absolute cold, approaching absolute zero, infinite dilution of all particles, and the complete absence of free energy. If you could somehow observe this universe, you would see nothing. No light, no heat, no motion. Just an endless expanse of nearly empty space, expanding forever, growing colder and emptier with each moment. This is the ultimate fate toward which entropy has been driving the cosmos. In this era, the average density of the universe will be unimaginably low. Right now, there's about 1 hydrogen atom per cubic meter. In the dark era, after countless ages of expansion and particle decay, there might be 1 particle per cubic light year or per cubic megaparsec, or even less. The universe will be, for all practical purposes, perfectly empty. Any remaining particles, whether photons or neutrinos or something else, will be so spread out that they effectively never interact with anything. They'll simply drift through the void, alone for eternity, stretched and redshifted by the expansion until they carry essentially no energy at all. The temperature of this universe will asymptotically approach absolute zero, but it will never quite reach it because the expansion prevents complete thermalization. The cosmic background radiation will have been stretched to wavelengths measured in light years or more, carrying so little energy that it's effectively nothing. But it will still exist, a faint ghost of the Big Bang, the last echo of a time when the universe was hot and dense. This radiation, once the afterglow of creation, will become the faintest whisper, a murmur so quiet it's nearly indistinguishable from silence. But even whispers persist forever when there's no sound to drown them out. In this state, the concept of space itself becomes strange. Space will continue to expand, but what does expansion mean when there's nothing to measure it by? If 2 particles are moving apart due to expansion, but they're so far away they can never see or influence each other, does their separation even matter? In a sense, each particle exists in its own isolated universe, causally disconnected from everything else. The cosmos will have fractured into an infinite number of separate, lonely domains. This is perhaps the most profound form of loneliness imaginable, existence without the possibility of connection, awareness without the possibility of experience. Quantum mechanics offers one final glimmer of activity in this dead universe. Quantum fluctuations, those random bubbles of energy that pop in and out of existence due to the uncertainty principle, will continue forever. They don't violate the laws of thermodynamics because they always balance out. For every fluctuation that creates a bit of energy, there's an equal and opposite fluctuation that removes it. But over timescales that make even the black hole era seem brief, these fluctuations could theoretically create structures. A random fluctuation might, by pure chance, assemble a star, or a brain, or even an entire universe. But such events would be separated by times so vast they're meaningless. Some physicists have speculated about Boltzmann brains, hypothetical self-aware entities that spontaneously form from quantum fluctuations. The idea is that it's more likely for a fluctuation to create a single conscious observer with false memories of a universe than to create an actual universe. In the infinite expanse of the dark era, Boltzmann brains would eventually form, think, a single thought, and dissolve back into randomness. They would vastly outnumber any real observers from earlier eras. It's a strange and unsettling concept, suggesting that most conscious experiences in the universe might be brief, isolated, and illusory. But this is the kind of weirdness that infinite time and space give rise to. The dark era will last forever, or at least as close to forever as makes no difference. There's no process that can end it, no event that can change it. It's the final chapter, the ultimate outcome of the laws of thermodynamics playing out across cosmic timescales. And in a way, this is oddly comforting. The universe doesn't end in catastrophe. There's no cosmic war, no collision with another universe, no supernatural judgment, just a slow, gentle fading away. The universe runs down like a wind-up toy, moving slower and slower until it simply stops. It's an ending that matches the scale and majesty of the cosmos itself. Patient, inevitable, most peaceful. But is this really the end? Or is it a beginning? Some theories suggest that if we wait long enough, long past anything we've discussed, quantum fluctuations could nucleate a new Big Bang. A bubble of false vacuum could spontaneously form and expand, creating a new universe with its own laws of physics, its own stars and galaxies, its own story to tell. Our universes. Heat death might be the seed for new creation, an eternal cycle of death and rebirth stretching infinitely into the past and future. It's an appealing idea philosophically, but based on our current understanding, it's purely speculative. For now, the heat death appears to be the true end, the final word in the cosmic story. Before we turn to the philosophical implications of the universe's end, let's briefly consider the other possible fates that cosmic destiny might have held. The heat death, or big freeze, is the most likely scenario based on current observations, but it's not the only possibility. Science is always open to revision, and new discoveries could change our understanding entirely. Throughout history, cosmologists have proposed various end scenarios, each with its own strange and compelling logic. These alternative fates remind us that the universe is far more mysterious than we often acknowledge, and that our knowledge, while impressive, is far from complete. First, there's the Big Crunch, the fate we once thought most likely. If the universe contains enough matter, gravity could eventually halt the expansion and reverse it. Galaxies would begin moving toward each other instead of away. Over billions of years, the universe would contract, growing denser and hotter. Galaxies would collide and merge. Stars would pack closer together. Eventually, everything would compress back into a state resembling the Big Bang, unimaginably hot and dense. Then, perhaps, another Big Bang might occur, initiating a new cycle. This oscillating universe model is elegant and allows for eternal cosmic renewal. But observations of dark energy have made it seem unlikely. Then there's the Big Rip, a scenario that occurs if dark energy not only accelerates expansion but grows stronger over time. In this fate, first, galaxy clusters would be ripped apart, then individual galaxies, then solar systems. Eventually, even stars and planets would be shredded as the expansion overcomes chemical and molecular bonds. In the final moments, atoms themselves would be torn apart, then atomic nuclei, perhaps even the fabric of space-time. The universe would end, not in a freeze, but in a catastrophic disintegration. Thankfully, current evidence suggests this is unlikely. Another possibility is vacuum decay. Our universe might exist in what's called a false vacuum, a state that seems stable but isn't the lowest energy state possible. If this is true, then at some random moment, a true vacuum bubble could spontaneously form somewhere in the universe. This bubble would expand at the speed of light, and anything it touched would be instantly destroyed and replaced with a region of space governed by different physical laws. Stars would cease to shine. Atoms would fall apart. Inside the bubble, physics as we know it would simply stop working. And we would never see it coming because it travels at light speed. There would be no warning, no last moment, just instant, total annihilation. There's also the possibility that our current understanding is simply wrong. Dark energy might not be what we think it is. Perhaps it's not a cosmological constant, but a dynamic field that changes over time, which could lead to outcomes we haven't predicted. Or maybe quantum gravity, a theory that successfully merges general relativity and quantum mechanics, will reveal new physics that changes everything. Black holes might not evaporate. Protons might not decay. New forms of matter or energy might exist that we haven't discovered. The universe is under no obligation to behave according to our current theories. We must remain humble in the face of cosmic mystery. Some more exotic theories propose even stranger ends. In certain models of string theory or brain cosmology, our universe might collide with another universe, a parallel brain in a higher dimensional space. Such a collision could destroy both universes or merge them into something new. Or perhaps our universe is a simulation, a computed reality running on some substrate we can't perceive, and its fate depends on whether the simulation continues or is terminated. These ideas are highly speculative, bordering on science fiction, but they remind us that reality might be far stranger than even our best science suggests. We live in an era of profound cosmological uncertainty. Despite all these alternatives, the heat death remains the most probable outcome according to our current best observations. We've measured the expansion rate. We've detected the presence of dark energy. We've seen no evidence of vacuum instability or extra dimensions. The universe appears to be heading toward a cold, dark, final state. But science demands that we remain open to new evidence, new discoveries that could change our understanding. Perhaps future observations will reveal something unexpected. Perhaps there's a twist in the story we haven't seen coming. Until then, we work with what we know, accepting uncertainty while building the best models we can. The study of the universe's ultimate fate is called physical eschatology, the science of cosmic endings. It's a field that combines astrophysics, quantum mechanics, thermodynamics, and even philosophy. Because when you ask what will happen to the universe, you're really asking deeper questions. What is time? What is existence? Is there meaning in a universe that must end? These are not just scientific questions. They touch on the very nature of being, on what it means to live in a cosmos that is temporary and finite. And that brings us to perhaps the most important part of our journey, the philosophy of cosmic mortality. Now, how do we find peace in the knowledge that everything will end? For thousands of years, humans have pondered endings. Our own mortality, the mortality of our civilizations. Now, with modern cosmology, we must confront the mortality of the universe itself. It's a daunting realization. Everything we know, everything that has ever existed or will exist, is temporary. The universe is not eternal. It had a beginning, and it will have an end. This knowledge can feel crushing, existentially terrifying. If everything ends, does anything matter? If the universe is destined to become a cold, dark void, why does the light matter now? These are profound questions, and they deserve thoughtful consideration. The ancient Greeks recognized the concept of entropy long before they had the science to describe it. They saw that all things decay, buildings crumble, bodies age, civilizations fall. From these observations, some concluded that life is futile, that we should embrace nihilism or hedonism, living only for the moment since nothing lasts. But others reached different conclusions. The Stoics, for instance, argued that the temporary nature of existence makes virtue more important, not less. If everything is fleeting, then how we act in our brief time matters deeply. The universe's eventual end does not diminish the significance of the present. It amplifies it. Consider a sand castle on a beach. You know when you build it that the tide will come and wash it away. Does that knowledge make building it meaningless? Or does it make the act of creation more precious, more meaningful, precisely because it's temporary? The universe is that sandcastle, built by the laws of physics on the beach of space-time, destined to be reclaimed by entropy's tide. But that doesn't diminish the beauty of the structure while it stands. Stars shine, planets form, life emerges and thinks and loves. These are miracles, not lessened by their temporariness, but made more valuable because they won't last forever. Some find comfort in the sheer scale of cosmic time. Yes, the universe will die, but not for trillions upon trillions of years. From our perspective, that's essentially forever. Humanity will be long gone before the first stars even begin to run out. Our sun has billions of years left. We have time, vast amounts of time to live and grow and explore. The heat. Death is so far in the future that it need not concern us in any practical sense. It's a theoretical endpoint, not an immediate threat. We can acknowledge it intellectually while living fully in the time we have, which is all anyone can ever do. Others find meaning in connection. We are not separate from the universe. We are made of atoms forged in stellar furnaces. We are the universe's way of knowing itself, conscious matter contemplating its own existence. When we look up at the stars, we're engaging in an act of cosmic self-reflection. The universe, through us, is experiencing awe at its own majesty. And that connection doesn't depend on eternity. It exists now, in this moment. Every thought you have, every emotion you feel, is the universe experiencing itself. You are a brief but genuine expression of cosmic awareness, and that has inherent value regardless of how long it lasts. The Buddhist concept of impermanence is relevant here. Buddhism teaches that all things are temporary, and that suffering comes from our attachment to permanence, our desire for things to last forever. The solution is not despair, but acceptance. When we accept that everything changes, that nothing lasts, we can appreciate things more fully while they exist. The cherry blossom is beautiful precisely because it blooms for only a week. If it lasted forever, we would take it for granted. The universe's impermanence, like the cherry blossoms, is part of what makes it precious. We live in a rare, beautiful moment when existence is possible, and that makes it sacred. There's also the argument that meaning is not given to us by the universe, but created by us within it. The cosmos doesn't have to be eternal for our lives to have purpose. We create purpose through our actions, our relationships, our pursuits. A parent caring for a child, an artist creating beauty, a scientist seeking truth. All of these acts have meaning because we assign meaning to them. The universe's eventual fate doesn't change that. We are meaning, making creatures living in a temporary universe, and that's enough. Perhaps the only meaning that matters is the meaning we create for ourselves and each other here and now. Finally, some argue that the universe's mortality makes our existence more amazing, not less. What are the odds? The universe could have simply remained in its initial state, a featureless soup of energy. Or it could have expanded too quickly for structures to form, or gravity could have been too strong, causing immediate collapse. Instead, through an incredibly delicate balance of physical constants and initial conditions, the universe became interesting. It formed galaxies and stars. It allowed for complexity, for life, for consciousness. We exist during a brief golden age when the universe is neither too young nor too old, when stars shine and planets orbit and awareness is possible. That's not a cause for despair. That's a miracle. Where do we stand in this cosmic timeline? We humans, with our brief lives and shorter civilizations, we exist 13.8 billion years after the beginning, at a time when the universe is still young and vibrant. Stars are still forming. Galaxies are still colliding and merging. The cosmic background radiation is still warm enough to be detected. We live in what future cosmologists, if any exist, might call the good times, the era when the universe was most alive. We're fortunate, in a sense, to exist now rather than in the cold darkness of the far future. But fortune is a strange word when considering existence itself. Our sun is a fairly ordinary star, neither particularly large nor small, neither exceptionally hot nor cool. It formed about 4.6 billion years ago from a cloud of gas and dust, inheriting its material from earlier generations of stars. Around it, planets coalesced, including Earth, a rocky world at just the right distance for liquid water to exist on its surface. And on that world, through processes we're still working to fully understand, life emerged. Single cells at first, then multicellular organisms, then animals and plants, and eventually us. Conscious beings capable of asking why we exist and what it all means. The emergence of life on Earth is still one of the great mysteries of science. How does non-living matter organize itself into living systems? We know it happened at least once here on this planet. Whether it has happened elsewhere in the universe is one of the most profound, unanswered questions. Are we alone in this vast cosmos? Or is life common, arising wherever conditions permit? If we're alone, that makes us incredibly precious, the universe's only chance to know itself. If we're not alone, that makes us part of a greater cosmic community, one we've yet to discover. Either answer is staggering in its implications. Life has existed on Earth for about 3.8 billion years, nearly as long as the planet itself. For most of that time, it was simple. Single-cell bacteria and archaea. But about 500 million years ago, complex life exploded in diversity during the Cambrian period. From that point forward, evolution produced an astonishing variety of forms. And just a few 100,000 years ago, humans emerged. We're newcomers, late arrivals to the party. If Earth's history were compressed into a single day, humans would appear in the last few seconds before midnight. We've barely had time to settle in, and already we're pondering the end of everything. What makes humans special, if anything? We're not the strongest animals. We're not the fastest or the largest. But we're the only species, as far as we know, that's capable of understanding the universe at this level. We can look up at the stars and comprehend what they are, how far away they are, how they were born, and how they'll die. We can trace our own atomic lineage back to stellar furnaces. We can predict the universe's fate billions of years hence. This capacity for understanding, for abstract thought and existential contemplation makes us unique. We are the universe's poets, its scientists, its philosophers. We give voice to cosmic wonder. Our individual lives are impossibly brief compared to cosmic timescales. An average human lifespan is about 80 years. That's nothing. A blink. The light from a distant galaxy, traveling for billions of years to reach us, existed long before we were born and will continue long after we die. We are ephemeral, here and gone in what feels like an instant from the universe's perspective. And yet, during our brief span, we can touch infinity. We can contemplate eternity. We can understand, even if we cannot experience, the vast sweep of cosmic time. Our brief lives contain multitudes of awareness and experience that transcend their limited duration. Our sun will eventually die, expanding into a red giant in about 5 billion years and destroying Earth in the process. Long before then, in perhaps 1 billion years, the sun's increasing brightness will cause Earth's oceans to evaporate, making the planet uninhabitable for life as we know it. Humanity, if it still exists, will need to move elsewhere, perhaps to other planets in other solar systems, perhaps to artificial habitats in space, or perhaps we'll have transformed ourselves so completely that we'll be unrecognizable as the species we are today. Or perhaps we'll be gone entirely, replaced by our descendants or our creations, or simply extinct, a brief experiment in consciousness. If humanity does survive and spread throughout the galaxy, we could potentially exist for trillions of years, migrating from star to star as each one dies, harvesting energy and resources, adapting and evolving. We might witness the universe's slow decline firsthand, watching as star formation ceases and galaxies drift apart. We might be there when the last stars flicker out. It's an overwhelming thought, both grand and melancholy. But more likely, if history is any guide, humanity as we know it will be transformed or replaced long before then. We are not the endpoint of evolution, but a step along the way. What comes after us might be as different from us as we are from bacteria. We've journeyed to the end of time and witnessed the universe's ultimate fate. Alas, the stars will die. The galaxies will disperse. Black holes will evaporate. And finally, after timescales that beggar imagination, the cosmos will settle into cold, dark, eternal stillness. It's a sobering vision. But it's also strangely beautiful, isn't it? The universe is not capricious or cruel. It's simply following the laws of thermodynamics, playing out a script written into the fabric of reality at the moment of the Big Bang. There's a kind of dignity in that inevitability, a sense that everything is unfolding as it must. The knowledge of the universe's end can be liberating rather than oppressive. It reminds us that nothing lasts forever, and therefore nothing is so important that it justifies eternal worry. Your mistakes, your regrets, your embarrassments, all of it is temporary. Not just in the sense that you'll eventually forget, but in the cosmic sense that everything will eventually fade. The universe itself doesn't judge you. It simply is, following its path from beginning to end. You are part of that process, a temporary configuration of matter and energy that has the strange privilege of being aware of itself. That's not a burden. There's a Japanese aesthetic concept called mono no aware, which translates roughly as the pathos of things or the beauty of transience. It's the bittersweet appreciation of impermanence, the recognition that things are more beautiful precisely because they don't last. The cherry blossoms, the autumn leaves, the sunset, all gain poignancy from their brevity. The universe itself is subject to mono no aware. Its beauty is inseparable from its temporariness. A galaxy spirals. A star shines. A planet orbits. These are all transient phenomena, and knowing they will end makes them more precious, more worthy of appreciation and wonder. We've spent an hour together exploring the universe's fate, watching as the cosmos transitions from vibrant chaos to ordered stillness. But let's not forget where we started. Look around you. Look at the world you inhabit. It exists in that brief golden age we discussed, when stars still shine and life is possible. The universe may be temporary, But right now, in this moment, it's full of light and wonder. You are alive during a time when you can see the Milky Way stretching across the sky, when you can watch planets move against the stars, when you can witness the births and deaths of distant suns. That opportunity won't exist forever, but it exists now. Wait, and that's what matters. Not what will happen in a trillion years. What's happening right now, in this precious fleeting moment. The universe's story is your story. The atoms in your body were forged in the cores of ancient stars that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar nucleosynthesis and supernova explosions. You are literally made of star stuff, as Carl Sagan famously said. When you contemplate the universe, you're not looking at something separate from yourself. You're looking at your extended body, your cosmic heritage. The universe isn't something out there. You are the universe, a particular arrangement of it, experiencing itself from a unique perspective. Some people find the idea of cosmic mortality terrifying. The thought that everything ends, that nothing ultimately persists, can trigger existential dread. But consider the alternative. What if the universe were eternal and unchanging? What if nothing ever evolved or transformed? That would be a kind of death too, a frozen stasis where nothing new could ever happen. The universe's temporariness is what allows for novelty, for change, for the emergence of new forms and new experiences. Every ending is also a transformation. The death of a star seeds new solar systems. The end of one era births another. Even the heat, death in some speculative theories, might be a necessary prelude to new creation. As we approach the end of our journey, I want to leave you with a thought. The universe doesn't owe us permanence. It doesn't owe us meaning or purpose or even existence. And yet, here we are, against all odds, through an intricate dance of physical laws and cosmic accidents, matter organized itself into forms capable of thought and feeling and wonder. You exist. You're conscious. You can contemplate infinity and feel awe at the cosmos. That's not something to take for granted. It's a privilege, a brief window of awareness in an otherwise unconscious universe. The heat death will come, yes, but it hasn't come yet. And in the meantime, we have stars to admire, questions to ask, and each other to share the journey with. The universe will end in silence and darkness, but it doesn't end today. Today, it blazes with countless stars. Today, galaxies dance in gravitational embrace. Today, somewhere on a small blue planet orbiting an ordinary star, conscious beings look up at the night sky and feel wonder. That's not nothing. That's everything. The fact that the universe is temporary doesn't diminish its beauty. It amplifies it. We live in a rare, precious moment when existence is rich and complex and full of possibilities. So instead of mourning the distant future's darkness, let's celebrate the present's light. Let's be grateful for the brief, improbable gift of awareness. Because we are here now, witnessing the universe in its glory. And that is enough. Thank you for joining me on this journey to the end of time. We've witnessed the universe's birth, its golden age, and its eventual quiet decline into eternal darkness. The heat? Death may seem like a sad ending, but remember that endings are what give moments their meaning. The universe is beautiful precisely because it's temporary. We're fortunate to exist during this brief window when stars shine and awareness is possible. As you drift off to sleep tonight or continue with your day, remember that you are made of stardust, that you are the universe experiencing itself. And in this moment, right now, the cosmos is very much alive. What mysteries will we uncover next time? Until then, keep looking up. The universe is waiting.